My name is Daria Dobrycheva, and I work in the main astronomical observatory. And it's in Kyiv, but originally I'm from Chernihiv, and I have two addresses, like I live in Kyiv, but in my heart, Chernihiv. And it is my address. But we have the same address with you. It's like our Earth. And the next one, it will be, you know, it's our galaxy. And it's not good light for here for see it, but it's an incredible photo. It's a Milky Way. Now we cannot see even in Lviv, in Kyiv, in Chernihiv, our address like a Milky Way, but it's a photo have done in Chernihiv by Chernihiv photographer, but unfortunately in terrible situation in the last March when my own Chernihiv was blocked by Russian terrorists, and 1 month this city without electricity and supply, and unfortunately in this situation photographer yeah. Oh, it's more, yeah. And I want to read the word of this photographer that it was my dream to shoot the Milky Way over the Katerinka. Katerinka, it is the cathedral in Chernihiv. However, I never thought that the lack of the light for this photo would be possible under such difficult circumstance. And closer to the next slide about different one of galaxies. Here you can see the different shape, different morphological types of galaxy. And as Sandwich say that the first step when you want to learn any subject, it should be work with the classification of it. Because when you classified some object, you can find some feature from this object, and in the next time work with this feature, understand more exactly the physics of this object. And astronomers use some different shape of classification, but here I propose you to see Hubble turning fork diagram, where we have elliptical galaxy in this one. In astronomy, it is very easy. If the shape of object closer to elliptical, it's called elliptical. And the brightness of this galaxy decreases from the center to the periphery. The next one is a lenticular galaxy. It is the middle between the elliptical and spiral galaxy, and it has large-scale disk. But this galaxy doesn't have arms like in a spiral galaxy. The next one, it is a spiral galaxy. And we have two types of spiral galaxy. First one, when the arm started from the center one. And the next one, it is beard galaxy, because here we can see the bar inside the central, and from this bar, arms started. And the last galaxy, not last, but in my presentation, it is a irregular galaxy. Irregular galaxy, it's also easy because it's irregular shape, not like a spiral or elliptical or lenticular. It's chaotic shape of this galaxy. And I work with the Sloan Digital Sky Survey. It's a very good example of how business can help to fundamental science, because it's Sloan, named by Sloan. Sloan was a president of General Motors. General Motors.
So the history of Sloan, it was when after he died, he set up a foundation that funded this.
Thank you. Yeah. It's incredible digital sky survey telescope, which 2 and 5 meter and in a wide angle optical wavelength. And here you can see reconstruction. These scientists have done it. He take images from SDSS and try to reconstruct the nearly universe. And here, every point, it's not a star, it's a galaxy, like elliptical or lenticular or any other of them. And it's SDSS. SDSS every night gave to us 200 gigabytes. Every night, 200 gigabytes data. But the next generation, one of them, telescope with LSST, will give to us 20 terabytes information every night. Every night, a huge, amazing information about our universe, and without this, without machine learning, I don't know what we will do, how to analyze all this information. And in this lecture, I will talk about the supervised learning method in machine learning, divided to unsupervised and supervised learning method. Unsupervised learning method, in this method we work when we know all feature about a data set and goal to explore the structure of this feature. And we use a lot of clusterization method. In supervised learning method, we know all feature from some part of the sample, but for another sample, we don't know this information, and we use, we should, with the help of this method, our goal to predict missing features. And this method used for a classification and regression. In my presentation, I will talk about only classification because I work and I present a result about classification. We will talk about random forest, nearest neighbor, support vector machine, logistic regression, and naive bias. In this part, I will talk about the, just a moment, about binary morphological classification, when we divided our sample into two classes. In our work, we divide it into early and late type. It's interesting, it's a historical name of this galaxy. We divided galaxy into early and late. It's like kids in the parents have kids and older and younger. And if it's older kids, it's early, and younger kids, it's later. Why such? Because late type galaxy, it's all spiral and irregular, have a gas. Gas, it's like a bridge for make a star. And elliptical galaxy has no gas, and we can do, not we, this galaxy cannot do a star. That's why early and late type. And in our work, we use SDSS release number 9. And first of all, it was 700,000 of galaxy, and we deleted all duplicates, some artifacts. Sometimes it's SDSS scan in the sky, and it's put like it is a galaxy, but it's empty place. And we deleted all of this, and at the result, we have nearly 300,000 of galaxy, and redshift to 0.9. And first of all, when you started to work with some object, you need to find the features. Features, it's some characteristic with the help of which you can divide this object to different type. And in Galaxy, we use a different photometrical parameters. For example, absolute stellar magnitude, it's a photometrical parameters which intrinsic luminosity of brightness of the star, including within the galaxies. It provides information about true brightness of the star or galaxy. And the next one, it is color indexes. Color indexes is differences in brightness at the different wavelengths. For example, early galaxies typically have a redder color. due to dominated older stars, while late type galaxies have a bluer color because they have dominated younger and hotter star. Also, concentration index to this to the galaxy, concentration index to the center. It's measure how much light from the center toward from the center toward to the periphery brightness decreases. And Cercic index. It is a parameter which characterizes the light profile of the galaxy. In early type, this parameter is generally higher. In the late, it is lower. And when we downloaded all these parameters from the SDSS and different band, we should too use a feature importance. Because it is very important to know how exactly different features improve your accuracy to identify this morphological type. In our case, we use a training sample, 6,000 of galaxy, and we, using feature importance, we identified that exponential radius, divocolor radius, redshift, inverse concentration index to the center, different color indexes, and absolute stellar magnitude, very important for classification of the galaxy. And now I'm running through the different classical classical machine learning method. First one, it is a random forest, is a machine learning technique that creates multiple decision tree and merge their prediction to improve the accuracy and reliable to find the result. And decision tree is separate data into groups based on different characteristics and determine which characteristic each element belong to. It's easy example here. We have data and we ask, is it red or not? If red is underlined or not underlined. And random forest, it's merged the result from many decision trees to produce a single output. If we can see in a decision tree, in a scikit-learn and random forest, we can see that a lot of parameters we have the same. But I want concentration in the different one. And first is a number estimator, number of estimator, number of feature, bootstrap sample, and out of bag error. First one, it is a number of estimator. This hyperparameter determines how many decision trees will be used to random forest ensemble. Each decision tree predicts the target class of value, and the result of the trees are combined through voting for classification. The next one is a number of feature. This hyperparameter divides the number of random features that will be selected for each decision tree. In random forest, the certain number of features are randomly chosen from entire set of features at each tree building steps. This helps to make a model more diverse and less prone to overfitting. The next one, bootstrap samples. Random forest employs the bagging technique, which means the random forests are drawn from training data sets to train each tree. It allows using the same data with repetitions and creating different data sets for training each tree, thus providing more diversity and robustness of the model. And the last one, it is out of bag error. Since each decision tree in a random forest uses only subset of data, some samples are left out of the training data for each tree. This unused sample can be used to estimate the model's error without the need for a separate validation data. And the next one is nearest neighbor. This algorithm is machine learning, which take prediction based on the majority, class, or average value of its closest data point in the feature space. Here you can see the example when we can easily separate it. And it's a color indexes and inverse concentration index to the center. And it's easy separated spiral and elliptical. But if we have some point here, what do you think? It will be spiral or elliptical one? Elliptical one, yeah, because it's closer to elliptical, yeah, right? It is very easy. But if here, it will be spiral or elliptical. Zero. But we should choose. Okay, it will be spiral because it's closer to the spiral. But if we take k near, we should choose 2 nearest neighbor. It will be also spiral because spiral galaxy is closer. But if we take k 3, we have 2 spiral and 1 elliptical. It will be. It's easy, yeah. It will be spiral because we have 2 spiral and 1 elliptical. But if we have 2 spiral and 2 elliptical, 2 spiral, it leads to tie. And we should go to the scikit-learn and read about warning in this situation. And the scikit-learn told to us that regarding the nearest neighbor algorithm, if 2 neighbors, chi plus 1 and k, have identical distance between the different labels, the result will depend on the ordering of the training data. And in the case of tie, the answer will be the class of happens in appear first in the set of neighbors. And also, results are ordered by distance. So it chooses the class, the closest point. The closest is spiral. Closer, spiral. That's why it will be spiral. And if we want a k value that minimizes error, in this situation, we should validate the grid search of multiple k value and choose k that result in lowest error or higher accuracy. Okay, the nearest algorithm first of all choose the k value, sort feature vector by distance matrix, and choose class based on the nearest feature vector. The next one, it is support vector machine. You had a lecture yesterday, and I want to say that in a n-dimensional space, a flat, about which we talked about yesterday, it is in a 1-dimensional, it is a point. In a 2-dimensional, it is a line, and in a 3-dimensional, it is a plane. If we have, as in a previous example, easy separated early and late point, it is very easy. We use a separate, maximize the merging between the classes. But if we have some galaxies located in another location, in this variant we use a soft merging, which allows support vector machine to make a certain number of mistakes and keep merging as wide as possible so that order point can still be classified correctly. This can be done simply by modifying the object of SVM. But here we can see an easy example when we can easily separate it to classes. But if in this example we cannot easily separate it, here where we can, no, it's not easy separated, but it's easy. In a support vector machine, you can use a kernel. Kernel is a project that can help to make a higher dimensional order. And here you can example how from 1-dimensional you can go to the 2-dimensional, and it is easy separated, these classes. Also, example in a 2-dimensional, we go to the three-dimensional, and it's also easy separated to classes. About a little word about C parameters in SVM. It's control the trade-off between maximize and merging and minimize the classification error. The large C value allows SVM to classify more data points correctly, possibly leading the overfitting. And a small number of C value prioritizes the maximize the measure, even if some data points are misclassified, possibly leading to underfitting. The next one, it is logic regression. Don't confuse if you see regression. It's still a classical classification, and in a logic regression we can model a morphological type of galaxy Y as a linear feature X. However, with a binary Y, this not straightforward, because this equation is a function that spans from the minimum infinity to the plus infinity, while Y has only two possible values. For binary morphological classification, we define a negative label as 0 and a positive label as 1, and we would need to find a simple continuous function, those domestic 0 and 1. And in this case, if the value returns by the model input x is closer to 0, then we assign a negative label to x. Otherwise, the example is labeling as a positive. One function that has such property is a standard logistic function, like sigmoid function. Here you can see. And the last classifier, it is naive Bayes classifier based on a naive theorem, conditional independent of the features, to calculate the probability of class. In our case, it is morphological classification and given a feature vector. And what about our work? Now we're running through all these 5 classifiers. We had a training sample which consists 6,000 of galaxies, and we decided to see, is it enough training sample in our case. And here you can see step by step when we plus it to training sample 100 objects, and you can see that 6,000 is enough in our case because we have a more than 90% accuracy, and for our sample it's random forest and support vector machine gave to us the highest accuracy, 95% and 96%. We can divide it sample into early and late galaxy using the different photometrical parameters. And the most, here you can see example of the correct classifier. It's early galaxy, it's late galaxy, like spiral, but we have an interesting misclassified galaxy. That's because we use a photometrical parameter. Photometrical different parameters, maybe someone don't know what is photometrical. In a simply words, excuse me, astronomer and physical, it is the light from the galaxy, different light. And if the big spiral galaxy, this spiral galaxy have a big bright center, and sometimes classifiers think that it is a big bright center, it's not a spiral, it's elliptical galaxy. It is the most spread misclassified sample in our work. The next one, I'm happy person because previous lecture was about CNN, and the rest part of my lecture will be about our work, not about CNN. In this part, we try to classify galaxy not into morphological classification, but using a shape. It is completely round in between, cigar shape, H-on, and spiral. We use here only images of galaxy and labeling, is it this shape or not? And we decided to compare our sample with Galaxy Zoo. Do you know, who don't know what is it, a Galaxy Zoo? Okay, it is a project where scientists ask to volunteers through over the world, please go to our site and see the images of galaxy and try to say, is it round, is it spiral, is it not spiral, and maybe some artifacts. And volunteers all over the world try to help scientists. And Galaxy Zoo have a database. We compared our sample, still 300,000, with the Galaxy Zoo. And we understand that we have a 170,000 of galaxy which match in a Galaxy Zoo. That means that we know the shape or morphological type of this galaxy. In the rest from our sample, it's not match in Galaxy Zoo. That means our aim is to find the shape of this galaxy. First of all, we decided compare it. Is it the same, this sample? Yeah, we decided comparing it. And we use photometrical parameters. It's magnitude in R band. And here you can see that this sample, Galaxy Zoo, and our inference, we call it inference, it's our sample where we don't know the morphological shape of galaxy. It is different. We're thinking about why it's different, and it's different because for this project, Galaxy Zoo, they proposed a bright, big galaxy for volunteers that it will be easy to visually identify which of this shape. In our aim sample to find the lower brightness this galaxy. And we decided to use adversarial convolution neural network to compare it with the help of CNN. Is it different or not? And our CNN say that this Galaxy Zoo part of galaxy and our infinity galaxy totally different in 90%. It means that we cannot use one part to training and another one to validate this data. That's why we took from the part of sample which was in a Galaxy Zoo, this which was the more closer by parameters to the infinity, which we should to identify. And it was 8,000 of galaxy, and 8,000 of galaxy, it's not enough for convolution neural network. That's why we decided to use a very good feature, maybe it's helped you in your work. It is adversarial augmentation. Augmentation procedure help to you to make a different. We have one images of galaxy and augmentation help to make, for example, smaller images, bigger images, different light of images, make some manipulation that from one images make a lot of one. And with help of this augmentation procedure, we increase our training sample and working with this. And we use a different CNN. Here you can see, and we found that training on this CNN, the density, dense net 201 give us the best result in a 96%, with the help of which we can identify 5 visual shape of galaxy. Here you can see not good, but result round it's 93%. In between in 93, cigar 75, H 93, and spiral 96. But it's interesting question why cigar shape is 75. It's the lowest one. we a long time thinking why even this galaxy have a lower result. Maybe you have idea? Yep.
My guess is that when you take an image of a galaxy, the image plane is not aligned with the galaxy plane. So some pictures may appear like edge on, and so it will look like a cigar when in fact when you rotate it, it will in fact be an elliptical or spiral galaxy.
But if you mean augmentation, yeah? When we work with a rotating the galaxy, yeah?
Well, yeah.
Yeah. Okay.
Like
It's a good
3D, so
it's good idea, but we don't use a 3D. We rotate it like in a one, one
so
another
you
way.
rotate it only in
Yeah.
Okay.
But it's a good idea, but it's easy because we read a chat about Galaxy Zoo, and we found that even cigar shape, it's not good classified in a Galaxy Zoo. That's why it's a based sample which we took from the Galaxy Zoo was not so good classified. That's why in our training, CNN also give to us not good result. Because maybe some volunteers don't understand where is cigar shape or in between. It's difficult to classify. And here, how we use a K-nearest neighbor. We took from our inference data set, and using K-nearest neighbor, we took a 5 from the Galaxy Zoo with the same parameters, and mean if 5 galaxy have the same parameter like this one, it is the same type of shape. And it is a very good example of round in between, H on, spiral, sorry, my eyes cannot, cigar, round in between, H on, and spiral. Yeah.
So are you training on single color band data or multicolor data?
Single.
Single. And I guess Galaxy Zoo is single as well.
Yeah, we took on the images.
So, but images are single frequency. So, R band probably was it Sloan?
No, we don't use a different band. We use only like.
Well, Sloan observes in GRIZY.
Excuse me. Yeah, you are right. We use
R band or I band? R band.
Yeah.
Okay. No, I'm just wondering because the pictures you show have color in them because there's the blue, but that's for our entertainment. But for the training, you're using single band.
No, we use we converted different band to the RGB images.
So you're training on so you're projecting. So the data is in a 5-dimensional space called image space.
Yeah.
And you're projecting to 3.
Yeah.
And then training on that 3-dimensional space.
Yeah. Thank you.
Okay.
I may ask, if you trained on the original 5-band image and just run CNN filters across all 5 bands, do you think you might have gotten better?
No, we use a 3-1.
No, I understand that. But if the original image is in 5 bands, then how do you know that running a 5-band filter across the 5 bands wouldn't give you better results in your CNN?
It's a very interesting question, but with a code, I like my colleagues work with this code and convert these bands to these images. And excuse me, maybe in the coffee break, I call and ask what the answer of your question. But this is very interesting. Thank you so much. And the last part, we decided to see intrinsic parameters. It's like, for example, artifacts, or how many arms inside the galaxy, or is the galaxy have a dust line, or it's a merging galaxy. In this variant, we took also this parameter from Galaxy Zoo and try using, as I said, the nearest neighbor. And if we take one galaxy which we don't know and use a 5 nearest neighbor which have the same parameter, and decided if they have the same parameter, it is a galaxy devoted to this band of images. And as a result, we have a very good result. For example, we have a intrinsic feature parameters. It could be arms, like 2 arms galaxy. We have a 78%, and in this sample we have 29,000 of galaxy. For example, bar, it is 77 and 20,000 of galaxy. Merging 70, it's a very good accuracy, we think, for us, and very good subsample of galaxies. And I want to show you our result. It's interesting that irregular galaxy, 70% it's an irregular galaxy, and 30% it is a regular galaxy. In this variant, our CNN work very good, because all galaxy which in a sample irregular, all with any accuracy, it's all irregular. It's interesting, because if you cut off a sample, for example, you need 50% accuracy. You cut it, but in this variant, lower percent, it's also irregular. The next one, it is dust line. It's more interesting, because we after took a result, we make a visual inspection of this galaxy, and we see that in even 10% with a dust line, it is this galaxy have a dust line. It is a bar, also very good. But in a bar sample, the next will be edge on, also work fantastic. Here you can see example where CNN say that it is bar, but it's not a bar. For example, it's look like more to irregular or very late galaxy, and it's not look like a bar. Or for example, here, it is overlapping to galaxy and overlapping visually. Yeah, it could be on a different distance, but core of this galaxy overlapping, and our CNN think that it is bar inside the galaxy. Merging is very good work. All of this sample in our example in our sample is merging. Except not merging. Yeah.
This is technologies of.
This percent, it is a result, yeah, of CNN.
What is CNN?
CNN, yeah. And this also a very good example when CNN think that it is merging. Here you can see a good example of merging, where 2 big galaxy started to merge. And here is not a merge. CNN think that this star, which on the images, it is another galaxy where they merge. Or for example, this very late spiral galaxy, it is have a very broad arms, and CNN think that it is 2 galaxy merging. Artifacts. These parameters very good CNN give to us result, because all these images have artifacts except not artifacts or star. Some part of this sample think that somewhere on this images there is artifacts, but it's not. It's a good example of galaxy. And
Isn't there an artifact in the upper right corner?
yeah, maybe here.
That's
And here maybe stars. Yeah.
I mean, it's getting the. I mean, there's an artifact in Sloan where the red and blue stars get displaced by diffraction effects, which
Really? Yeah.
which I think it's doing. It's picking up those diffractions effects.
And I going to the end, but before I say you thank you, I want to thank you my colleague. We work together, and he from the first time of war go to the army, and he was in a hottest part of the front. He was in Kiev, after that in Mykolaiv, Kherson, Kharkiv, and 2 months ago they came from the Bakhmut, and in a few weeks they also go to the front. I want to say thank you, Maxim, and also a lot of colleagues who now on the front, and all military. With the help of them, we here alive and can speak about Galaxy. Thank you so much.
Now, coming from one of the original Sloan institutions, well, we built the camera at Princeton, right? Jim Gunn started there. So Zsolt Fry was one of our students. I was on his thesis committee. So it's really neat to see this. So just it's very, so when you're doing the your training data is higher signal to noise because it's more luminous galaxies in Sloan than the data you're testing on, right? And this is a problem we're going to face in spades with LSST, but as well as billions of galaxies to classify. When you augment the data, have you tried putting in additional noise on the training data to sort of simulate the lower quality of the data?
And I want to ask you if you from because in the last version of SDSS, our sample was 700 of Galaxy and an eye release, but we saw that a lot of spams, like duplicates, a lot of duplicates. When I was in a first year of PhD, I spent 1 year to cleaning a sample because it was 700 of 1,000, and then the rest it was 300 of 1,000. I deleted all the duplicates. It's look like SDSS give to us that it is different galaxy, but it's a little bit shifted, and it is the same. It's so interesting.
There we go.
It's very interesting. But now as I checked, it's solved this problem automatically. And now if you downloaded data from the SDSS, it will be without this point. And you needed spend 1 year to cleaning a sample.
I have question for machine learning type at percent types. What is correlations of the types, and why this percent is more higher than another term? Random forest, k-nearest support vector machine. Just moment. Yeah. Yes, at that types. What is correlation, and why is that percent is that numbers?
Actually, about correlation, I don't know, but it's your play with this all classifier. I think maybe these parameters, photometrical parameters and images, more sensitive in this classifier. That's why we have here higher accuracy. But as you can see, it's most of all these classifier give to us a good result. It's 94 or 95. It's not so big. Different, yeah, except the naive bias.
Yeah, random forest or support vector machine. what is correlation of type of result, разница в результатах. Чим отличається random forest от support vector machine, тобто точность корреляции, разница точности корреляции. Ну, да, это проценты, а как они получились?
It's a good question. Maybe we...
Почему именно 95,5, почему не 93,2, почему не 91,8, то есть, ну...
Це кількість правильно ідентифікованих у відсотках.
Але ну, тобто, різниця між, ну, тобто, між machine learning, тобто, який найкращий, тобто, за якою технічною складовою вони порівняються?
I need maybe more time to thinking to answer your question. Maybe we discuss in a coffee break. But it's intrinsic parameter of all this.
My understanding what is the type of information you are integration as formulas, and you have results. I don't. I work in support vector machines in other project. I understandable what's the type of information and formulas that sphere, but I don't work in another sphere. And what is type of information you are includes that formulas and you have results.
Oh. In a random forest, very important these parameters, which I told a lot of example. It's very important number of estimator, number of feature, bootstrap sample, and out of back. And you playing with these parameters, you can inside the scikit-learn when you work with these parameters, you can put in write.
I guess the question is which features give so difference in accuracy, probably. It's not my question. I guess the question is what features?
Maybe.
Okay, so another question about classical ML. If you go back to the slide with the accuracy for these methods, they actually seem like very high, so around 96, 97%. So do you actually get a major boost from switching to neural nets? Because it seems about as high as it can get.
You mean like what the different, why a classical machine learning give to us a more accuracy? It also depends from in a classical machine learning, we use a photometrical parameters. In a CNN, we work with images from Galaxies. And it's very important that in a classical machine learning method, in random forest support vector, we have done a visual inspection by our eyes, and we work with this training sample, and we have done this classification. In the support vector CNN, we work with a Galaxy Zoo, and we took a classification from Galaxy Zoo. It is a volunteer. That's why we have a such low accuracy with cigar shape. Yeah, maybe that's because we work, not volunteer. Thank you. Thank you.
Thank you. It was very interesting. Question about the second part when you use the photo of galaxies. We don't know the accuracy of voluntary words. So if we have the accuracy of our model not so good, so the big errors, and then we multiply it in the accuracy of voluntary words, we have unpredictable state. So is it so good to use voluntary words as matching of the pictures. It's a problem because it damages all the results. Sorry for this question, but
it's a very interesting question, and how it's important to use a volunteer is it's very important because if you can see that in a galaxy zoo we took 170,000 of galaxy, and this galaxy volunteer have made a visual inspection, and no one galaxy for one volunteers. A lot of volunteers look in one galaxy and put it which one of that. And after that, also in a galaxy zoo, there is a procedure how to choose the best accuracy for this one. And in our case, we cannot find a lot of students who work with us together to make a morphological classification of 170,000 of galaxy to make a bigger accuracy. That's why sometimes it's lower accuracy than we want to have, but we cannot another choice. Maybe we will find a more better classifier or more majority project like Galaxy Zoo and how to interpret the result of volunteers. But we have what we have.
So first of all, thank you for a nice talk. And my question is about the first part of the presentation. So you showed us a nice slide where the elliptic and spiral galaxies created two clusters. Previous. What? No. It was a demonstration how two classes of galaxies, spiral and elliptic, create some two clusters if you look for two parameters. It was somewhere in the beginning. K nearest something. Yep. Yeah, this one. So my question is, in the beginning of the talk, you said that irregular galaxies is something that just look irregular, and my question is, if I put here irregular galaxies, will they create some independent cluster, or will they be distributed somewhere all over the plot?
That is very good question. I start about that we have a binary morphological classification. We divide it to early and late galaxy, and that's why we decided to grouped all elliptical and lenticular galaxy in one group, in another one spiral, beard spiral, and irregular in another group. But if you want to separate it, all these galaxy like elliptical, lenticular, spiral, and irregular, you should find we should find photometrical parameters which give to us the difference between these two classes. This photometrical parameter we will use in a classifier, and that's after that it will be in another place. But here we divided only two classes. That's why if we took a irregular galaxy, I think it will be something here.